Good afternoon. I'm Mayank. I work at University of Science. I'm also one of the co-founders of AlGaN Semiconductors Private Limited and also instrumental in setting up India's first gallium nitride fab in IISc. All the work done here are done by my PhD students. So, some of them graduated, some of them are around. You can meet some of these PhD students in the poster session. So, here as the title mentioned, I will talk about the challenges the pGaN gate based E-mode HEMT technology, though the commercial GaN HEMT technology is pGaN gate based. But I will talk about the challenges in developing this technology. And can we address these challenges by doing something more simple using a different kind of gate stack engineering. In this talk, I will also touch base briefly on some of the reliability aspects. We have done a lot of work on reliability, but I'll briefly talk about some interesting things we have found with aluminum dioxide based passivation. And towards the end, I'll talk about some of the bigger plans that we have that we are working on. Okay, now why since the community in this workshop is primarily microwave, RF and others, I thought of keeping some slides on why we are looking for power transistors, what aspects are needed for power transistor, and why we are always trying to improve power transistors. So, if you think from the system point of view, say if you have these 6 parameters, you always try to push the chart towards the right hand side, which what does mean? It means, so what does it mean is you have to basically reduce the cost, you have to reduce time to market, you have to reduce the losses at the system level. At the same time, you try to increase the power density, you try to increase the switching frequency, and you try to increase or improve the reliability. Now, in this context, people do explore different device geometry as well as different material potential materials, semiconducting materials for these power transistors. Among those 3 potential materials, I have not listed gallium oxide yet because this is still too far from being commercialized. So, those 3 materials which basically are commercialized in terms of having these power transistors out there: silicon, silicon carbide, GaN. If you compare these 3, GaN offers the best figure of merit trade-off in terms of on resistance and breakdown voltage. So, if you can really beat some of the technological and science problems which I will briefly mention later, you can achieve much better on resistance and breakdown voltage trade-off with gallium nitride. And if that happens, what you can achieve is, theoretically you can achieve 20 times faster switching at the system level. You can have systems which are 3 times smaller and lighter. You can have 40% better energy saving, up to 3 times high power density, 3 times better fast charging, and of course 20% lower system cost. But again, these are all theoretical predictions, and the whole objective of doing science with GaN is that how much we can get closer to the theoretical predictions or theoretical projections. Now, GaN also caters to, I do not want to say that GaN will replace everything, anything and everything, like the previous chart would tell you that GaN looks better than silicon, silicon carbide, but again GaN is going to cater to a certain kind of market segment. And what is that market segment? That market segment is, for example, from few watts or say few hundred watts to a few kilowatt kind of a market segment. That itself is a much bigger market segment, and if that happens, GaN has a potential to replace silicon. I'll talk about later that earlier this projection was that by 2020 the GaN is going to replace silicon. This has been pushed to 2026 because of serious reliability challenges, but if that happens, GaN has potential to replace silicon with the projected market of $1 billion by 2026. Now, before I get into the content of this talk, what is important? We are talking about power electronic systems. In general, if you look into any power electronic system, you need a transistor which is normally off. You need a transistor which is enhancement mode. Depletion mode transistors cannot do anything in a power electronic converter, right? So, we are talking about an enhancement mode transistor. Now, let us look into the possible options which are available out there to realize an enhancement mode transistor, right? You have pGaN gate based transistor technology, the first one that you see here. This uses a pGaN. So basically you do the AP stack, you grow the AP stack with a pGaN cap on top. Typically it's 70 to 80 nanometer pGaN cap with doping concentrations in the range of few E18 to 1E19. Active concentration would be around 1E17 to 3E17, right? Now this depletes the 2DEG and you basically realize these enhancement mode devices. But there are a lot of challenges out there. For example, you can have magnesium out diffusion into the barrier layer. You can have hydrogen complexes if you are using a hydrogen based process. You will have to do the pGaN selective etch. The source drain contacts are not as straightforward and done in the same fashion as you do for the depletion mode devices or the other type of devices. You get a weaker gate control here because of the 70 nanometer thick pGaN sitting over there. You have lower drive currents because you have to deplete 2DEG. You cannot start with a very high 2-deck concentration. So even the stack is realized with 2-deck concentration, which is almost half of the depletion mode GaN wafers, or half of what what practically you can achieve in a depletion mode configuration, AlGaN GaN stack configuration, which leads to lower on current, and you have low AlGaN barrier thickness, so it can also lead to gate leakage. Gate leakage is also introduced further by by the pGaN sitting on top of that, which limits the gate voltage to 5 volts. You have also complex process integration in thermal budget. I'll elaborate on this a little bit after a few slides, but let's talk about the other options that we have. Recess gate is one option, but that significantly degrades the on-state performance, and the performance is a strong function of the quality of the recess that you make. Since the recess quality could be anything, the reliability in this case also becomes a strong function of the recess that you make. The other option, the third option, is you can do say certain p-type implants, in this case fluorine ion implants under gate, but after a lot of work it was figured out that fluorine ions are not very stable, and particularly under high temperature or high field stress scenarios, and therefore you cannot basically practically use these devices for power electronic systems. Cascode is another commercial option which is present out there, but in this case the failure is governed by the low voltage silicon fed there, and also these devices tend to have much high gate charge and parasitic inductance because of the wire bonding between the D mode HEMT and the silicon transistor out there. Now let's look into, before getting into the process complexity of pGaN gate based transistor technology, let's briefly look into the typical process flow. So you start with in this case the wafer that you get has the pGaN grown on top of AlGaN everywhere. So it's basically a stack where you have GaN, AlGaN and pGaN which is present everywhere, and if you have to make a transistor, what you have to do, you have to keep the pGaN only in the gate region, which means you have to do a partial a selective recess, a selective etch of the pGaN layer there. Now we figured out after a lot of optimizations that if you do this by masking with a PR, the plasma process damages the top surface of pGaN, which leads to a lot of leakage related issues. On top of that, if you are doing it in 2 steps, then alignment of the top metal with the pGaN also becomes difficult. So if the metal falls outside, you have leakage issues, or if you try to reduce that metal, then you have the sidewall, the gate control from the sidewall will be pretty weak, and therefore it is going to affect the drive current. So which means you have to have something which can be used as a gate metal as well as a hard mask for this etch. But again, choosing the right metal is also very important, because some of these metal can basically go back in the plasma chamber and can become contaminant for other kind of process that you run. So once you have the pGaN etch, again what kind of pGaN etch? If you etch the pGaN and also start etching the AlGaN, then you have a problem, because you are going to deplete the 2-deck in that excess region. And if you leave the pGaN say if you partially leave the pGaN, again the p-type doping is going to deplete the 2-deck in the excess region. So in both cases you are going to lose in terms of performance. I'll also show you later on that there are some other issues because of leaving the pGaN out there. So a selective etch, developing a recipe which is selective etch is also very critical. And so it's not very straightforward, it's not very simple that you etch and you don't etch AlGaN, and the moment you touch AlGaN it stops automatically. So I mean, then we have MESA etch, which is not that difficult. Source drain contact. So in this case what we found that no matter what you do, if you are not doing a recessed source drain contact, you are not going to make good ohmic contacts. You will always have very high resistive contacts, most of the time Schottky contacts. So you have to develop a recess recipe for these contacts, and in this case we are talking about just few nanometers of recess. So a highly controlled etch, where if you are etching 4 nanometers, you are only etching 4 nanometers throughout the wafer, which is also very difficult. So we have to develop a cyclic etch process where we can control the etch depth based on number of cycles, and you actually program number of cycles than the time for which you etch. The source drain metal deposition, okay, this is straightforward, but again the kind of ratios and the stack that you use for D mode would not work here, so you have to re-optimize this. The annealing conditions, since this is a recess device, a recess source drain contact, the annealing conditions could be different. And then of course then you have to go further, you have to have passivation. In this case, since you don't have a GaN cap, you are etching and now AlGaN is exposed, you have to have a passivation, and the passivation has to be optimized for your 2-deck to behave properly. And then you have field plate design. We have published a lot of papers on this aspect also, that field plate design has to be done while keeping in mind the stack type, the kind of trap configuration in the buffer, the sheet charge concentration, and the kind of passivation in the surface trap configuration over there. So field plate design is also a complex process here. And then since we are talking about high voltage and high current devices, we are talking about tens of amperes of current, the back end of the line development is also equally challenging, which I'll talk about a little later. Okay, so let me elaborate on some of these points that I said. So magnesium out diffusion, so what happens is the pGaN doping, the GaN is doped p-type by magnesium. Now this magnesium can diffuse out at a certain high temperature. So if you are running high temperature processes, then you will have possible magnesium out diffusion into the barrier layer, AlGaN layer, and then that is going to further deplete the 2-deck. Which is something you have to avoid, right? And that's very difficult to avoid in this case, which means you are talking about developing a process which is a low temperature process relatively compared to D mode kind of a stack. Hydrogen complex, if you have hydrogen complex formed in the pGaN, then the magnesium, the active p dopants present in the pGaN layer will become inactive, and therefore the depletion which was present or the p-type doping concentration which was present will basically vanish. So you have to avoid processes which basically are rich in terms of hydrogen, or if you have done such processes, you have to do a different kind of anneals to get rid of those hydrogen complexes. Selective etch is what I mentioned about earlier, that you cannot do a partial etch, you cannot do an over etch. So you have to develop a process which basically gives you complete etch of pGaN without removing the AlGaN, right? And in that process, if you have variability across the wafer, you're going to see different kind of transistors with different kind of performance numbers all across the wafer, right? So this further adds to the complexity. Source drain contacts also, as I said, if you don't control this recess depth properly, the contact will vary across the wafer. So say if the optimum says you have to have 4 nanometer recess, and if that variation is 4 plus minus 2 nanometer across the wafer, your contact resistance is going to basically vary from say 0.7 ohm millimeter to say 2 ohm millimeter, right? That's a big number across the wafer. Then the thick pGaN leads to weaker gate control. I have already talked about the low on current, so typically you get 200 250 milliamp per millimeter kind of drive current. This technology is also limited in terms of the gate operation, so the gate voltage is limited by the diode which is formed, so beyond 5 or 6 volt you cannot operate the gate, which means at the system front you also need different kind of drivers. So the conventional gate drivers are designed for silicon MOSFETs, silicon carbide MOSFETs, where the switching is in the range of 0 to 20 volts. Now we are talking about designing new gate drivers which should be limited to 5 volt kind of operation, right. As I said, complex process integration, even the gate requires the spacer process to avoid any sidewall leakage. So even the sidewall, when you etch the pGaN, you have a lot of these sidewall traps. So these sidewall surface traps can also conduct, so you have to even passivate those sidewall surface traps. Thermal budget, as I said, a lot of these processes are low temperature process, and if you don't control or optimize the thermal budget, you may have other kind of problems. For example, in this case, the quality of tinitride. So we have this tinitride gate, and if you don't control the tinitride gate quality in terms of the contaminations, you have these kind of bubbles formed when you do a high temperature process. Now in terms of transistor performance or the sheet resistance, there was not much change, but if you don't notice this, you have these kind of issues formed when you do a high temperature process, right. So a strict optimization of the gate metal or the source drain is also important. So for example, if you see in the previous slide, you see the source drain metal region as well as the gate metal region, the quality is not that good, but when you do this strict optimization in terms of contamination control of carbon and oxygen across these metal stacks and proper recess optimization, you get much better quality source, drain and gate. Okay, so the other aspect I was talking about was the selective etch of the pGaN. So there are a lot of chemistries out there. You can use chlorine based chemistry, you can introduce oxygen and all, and what we found that you have to basically use a chemistry which starts creating aluminum oxide the moment it sees AlGaN, and that can become as a stoppant layer for any further etch. So we developed an etch and a chemistry, and what we could get here is this kind of etch. So if you increase the etch time, at one point you don't see any further increase in the etch depth, and that basically is when no matter how long you continue the etch depth remains the same, which means now it has basically saturated the etch. So you need a chemistry like this, which I can tell you required a lot of runs and optimizations to get to this point, and once you have that, then you can completely remove pGaN from wherever you don't want it without having any variability like issues. Now I was talking about if you don't optimize this well, you may end up having serious variability issues in terms of sheet resistance and contact resistance. And if you under etch, the other way is that you may under etch, right. Okay, let's not etch completely, let's under etch. But if you under etch, what we found that if you under etch, which means you are leaving some pGaN out there, you have serious dynamic R-on kind of issues, whereas if you do a full etch, there is no dynamic R-on kind of issues. Similarly with the contact, you have to find the right recess depth, and if you don't recess, you will never get a ohmic contact. Only if you recess you get ohmic contact, but then you have to have very tight control on the recess depth. So you have to do a lot of optimizations and make sure that statistically these numbers are giving you the performance parameters, not just getting 1 or 2 data points. Now though this is applicable to other kind of D-mode based high current devices as well, but in general for any power device you also have to do lot of you have to put a lot of effort on the back end integration. So for example, I talked about the front end of the line integration and challenges, but let's talk about the back end. For example, in case of back end, you need to ensure that there is uniform current distribution. I mean, we are dealing with, say if you are talking about 30 amp current device, we are talking about around 200 fingers, where each finger would be a millimeter in size. Let me correlate with typical RF devices. Typical RF devices, we are talking about say 100 to few hundred micron finger width, and maybe few tens of fingers depending on the kind of power you are dealing with, right. So compared to that, this is possibly 50 times bigger in terms of the size and area and therefore the complexity, right. So what we are talking about, you need to ensure that there is uniform current distribution across the device. There is stress induced because of these metals, and we are talking about thick metals. We are talking about 5 to 7 micron aluminum and copper, and 1 micron vias all sitting on top of each other, right. We are talking about interlayer dielectric, which is more than 1 micron thick, because we are dealing with breakdown voltage in the range of 600-700 volts, right. So there should not be any vertical breakdown or breakdown because of the metal crossing. Self-heating effects are also something very important to be addressed here. We are dealing with a lot of power inside the device, lot of current inside the device. Then there are boundary conditions imposed from the packaging side. These packaging, for example, if you do a TO20 kind of a package, right, not just wire bonding but the complete package with encapsulation, with molding and everything, right. So you have to account for those conditions as well and ensure that the device does not fail when the device goes through those kind of stress or thermal cycles during the packaging process, right. So we have developed the entire back end of the line. So as I said, there are all these challenges. So for example, if you have these thick metals and if you do any high temperature process, in this case I am talking about more than 300 degrees C, you have delamination kind of issues, right. These are thick metals, so there is a lot of stress also between the metal layers, right. Then thermal mismatch between different metals, so you have to choose right metals which basically have better adhesion to each other and also less thermal mismatch with each other. We are talking about processes where we are lifting off several microns of aluminum and copper. We tried all kind of processes. We tried even electroplating and whatnot, but then with these kind of thick metals and the kind of areas we are dealing with, electroplating does not work so well, and the quality of the electroplated metal then does not suffice the boundary conditions imposed by the packaging. So we had to live with the standard processes. We are talking about sputter, metal based on deposit by sputtering techniques, and we are talking about 5 micron aluminum or copper, and then thick oxides as interlayer dielectrics, right. And of course, if you are doing a copper process, then you also have to choose. You also have to basically have the right copper diffusion, in your back end of the line. So this is some of the pictures of our thick metal back end of the line process. This is 7 micron metal, 7 micron copper. So finally, we have the technology. We have these pGaN gate based E-mode devices, and as you can also see that the variability across the wafer is also quite negligible, and we are in the range of 250 milliamp per millimeter kind of a drive current at a gate voltage of 5 volt, where if you see data across 150 160 devices, the variability is within plus minus 10%, right. But this was lot of process run, expensive optimization, tighter process window, right. The question is, can we simplify this? Now let me tell you that the pGaN work is more latest than what I am going to present, but now we have experience of developing both the technologies, and that's why I'm going to talk about that. We have developed one technology which is very complex, very difficult. I mean, that's latest, we have done it now, that's also something which is out there commercial, and the other one is something which is our technologies, we discovered, we invented, and we know that the other one is simpler, so why not the other also gets commercialized, other also gets that kind of a push. Okay, so but let me stick to the storyline. As I said, this pGaN process is extremely complex, right. And so what do I mean by something being simple and yet best? Something simple means something which offers the best of D mode as well as the E mode. In terms of process complexity, it offers the best of D mode. In terms of the usability for systems, power electronic systems, it offers the best of E mode, right. So we are talking about relaxed process window and integration like D mode HEMTs. We are talking about high performance like D mode HEMTs, so performance better than 200 milliamp per millimeter. But at the same time, I am talking about off-state operation and high switching reliability, very similar to E mode HEMTs. right. So the idea was, and I can tell you later on that it was an accidental discovery, but here the idea is, so after that accidental discovery the idea was this, that if we have a p-type oxide, can I replace the pGaN in this kind of a stack with a p-type oxide, right. So if I replace the pGaN, or if I have a p-type oxide, I can basically do the same thing that the pGaN gate based transistor does. So let me talk about the p-type oxide. There have been several p-type oxides discussed in the literature, like copper oxide, nickel oxide. They have been shown to offer a positive shift in the threshold voltage, but the control on the threshold voltage is often very difficult, and since they have lower band gap, they basically lead to high gate leakage, and also not in real terms not an E mode operation. You see a positive shift in the threshold voltage, but not a positive threshold voltage yet, right. So then we because of this accidental discovery, we started exploring this idea that what if you dope tioxide with aluminum oxide, or in principle what if you dope tioxide with aluminum, or in this case what if you alloy tioxide with aluminum oxide. So if you look into this reaction diagram, what it leads to negatively charged aluminum sitting at tie sites, it leads to positive charge oxygen, vacancy sites, the oxygen vacancy site, so which basically results into the neutral oxygen vacancy and the holes. These free holes basically make the oxide p-type, right. So now we have a p-type oxide which can be used, and here the p-type characteristic, or the extent to which it is p-type, can be controlled by the amount of aluminum in the tioxide. So amount of aluminum alloying you do in tioxide. So we did some computations to figure out whether like pGaN, would it work in this case, and we studied at that time the thickness as a variable, at what point the charge is sitting, or in the energy space at what point the charge is sitting, which means how far or how close the Fermi level is from the valence band in case of the oxide. And as you bring this closer and closer to the valence band, you see even in the GaN region, the Fermi level shifts away from the conduction band, which basically is equivalent to depleting the GaN layer from the 2-deck, right. And we also investigated thickness, what kind of thickness you need, and what kind of energy separation you need. So this is the simpler D mode like process, where you have the source drain first. So you do the source drain contacts, then you have the gate stack deposited, and in this case what we did, we basically, even for improving the source drain contact resistance, we had developed a resist contact here, and then we had also developed a gate stack where the partial recess of the gate region was optional, and I will tell you later why the partial recess of the gate region was done. So it is a simpler process compared to the pGaN process, right. And in terms of the gate oxide, how we achieve it, so we basically did a cyclic ALD deposition of tioxide and aluminum oxide. So basically so you can program this in the ALD chamber. So you have few cycles of aluminum oxide deposition, and in the same chamber you have few cycles of tioxide deposition, and then you repeat it, right. So in this way you alloy tioxide with aluminum oxide, and depending on the ratio of N1 and N2 here, you can control the percentage of aluminum in the overall stack that you develop, right. So if you see here, depending on different cycle configurations, you can see the percentage aluminum varies. So we can control all the way from 0% when there is no aluminum oxide to 50%, 52% when basically it is done in equal proportion. Okay, so now you see this. So as we go from tioxide, when the threshold voltage is around minus 4.5, and as you increase the aluminum percentage from 20% to 52%, you get a 3.8 volt shift in the threshold voltage. And you also see, in all charts we always present the variability data. So if you see the data here presented is, if I remember correctly, at least 50 to 60 devices measured across the wafer, ensuring that we highlight the fact that this is consistent across the wafer and it's not just some accidental one device data that we have. So I have only 5 minutes left, so I'll skip few slides. So we did a lot of optimizations in terms of activation of these charges. What is the right temperature at which they will activate. We compared with dioxide. We also compared, the data is not in this one, we also compared with nickel oxide and copper oxide gate dielectrics. So what we found certain points where the threshold voltage was very high. We also pointed out that this still gives you a high K behavior. So even for 52% of aluminum, the K value was around 18 or 19. So this is 3 times higher than the K value of aluminum oxide, right? Yeah, so this is the comparison with copper oxide and nickel oxide, and if you see, compared to, nickel oxide was giving very high variability and copper oxide gives very high leakage compared to the dielectric that we developed, right? And so now we were around minus 0.5 volt of threshold voltage. This is for the case when the 2-day concentration is very high, meant for D mode devices, very high current devices, right? So now we have to shift the threshold load further. So there we investigated that if you reduce the 2-day concentration by thinning the barrier locally in that region, you can further shift the threshold voltage, and that's where we basically we then developed we introduced the partial recess in the gate region, and this is partial recess. So you're not fully removing the 22 nanometer of AlGaN, you're only partially removing AlGaN here, and that gives you further shift towards positive threshold voltage, right? So if you see on the other side, now if you recess from 22 nanometer to 8 nanometer, this is still, you are too far from the 2-deck, which may affect the leakage. You are now in the positive threshold voltage regime, right? Now if you see the drive currents, there is no self-heating issue, there is no dynamic R-on issue, there is no trapping issue. As you see the hysteresis plot there is no trapping issue in the gate dielectric, right? And we for 600 volt breakdown voltage, we are getting very low on resistance, 8.9 ohm millimeter for a 600 volt breakdown voltage device. So we also compared with best numbers reported elsewhere. Right, so there's some breakdown data, and we also did some state of SOA characteristic, and we found that because of the certain field configuration changes, the partial recess device with aluminum dioxide gives you better safe operating area compared to the previous one. And then we were parallelly studying the dynamic R-on, the physics of dynamic R-on, and what we found that our devices where the aluminum dioxide gate was used, now the way the gate is done is you basically remove the in situ silicon nitride and then do this ALD aluminum dioxide. So the aluminum dioxide is also sitting in this region, and what we found that these devices had much better dynamic R-on compared to the devices where only silicon nitride passivation was used. Now this was very interesting. In this case you see the dynamic R-on shooting all the way after critical voltage to several 100% in terms of increase in the on resistance, where here everything is less than 5%, right? Nobody reported these kind of numbers yet. So we published another paper on that, the details are there, but what we found that the aluminum dioxide, because of the p-doping, also helps distributing the field, and depending on the amount of acceptor trap concentration, you get a different kind of distribution, and as you go higher, the field spreads all across the axis region. So this is confirmed by the EL intensity graph here, where you see the case when there is aluminum dioxide, the field is all uniform across the axis region, unlike the other cases where the field is peaking at the gate side. So this is what we did. I will take 2 more minutes for few extra slides. In principle, what I told you was p-type oxides like aluminum dioxide brings excellent opportunity. I would like all of you to explore that. It basically offers much easier integration, it's cheaper process, high performance. We are talking about 400 milliamp per millimeter current versus 200 milliamp per millimeter current, right, and potentially better reliability because of some of the aspects I told you, like dynamic iron. The question is, can the advance, can we use this approach for developing commercial E-mode technologies? Now, I just want to run you through the major developments which happened in IISc, which I was leading. So, the aluminum dioxide work was supported by phase 1 funded by DST, and the pGaN technology is being supported by the phase 2, where we are also going to develop using our devices, these 1 kilowatt and 3 kilowatt fast chargers. We also started Agnit Semiconductors Private Limited, and Geeky, as I said, is the GaN fab, and we are also collaborating with CDAC, where they are helping us with the system development together with few other colleagues in IISc, and eventually Aether Energy has promised to take these systems and put in their electric vehicle scooters, right. So, this was our phase 1, where we converted this to a 4 amp 650 volt device technology. And now in phase 2 we are building a 30 amp 650 volt power GaN technology, where the idea is to basically take it all the way to qualified package device. We are also building systems, integrate into the systems, and also integrate that into these electric vehicle scooters and test it in the field. The last part in the phase 2 that we are working on is bridging the science gap or bridging the reliability gap. So if you see, as I told you in the beginning, this is the GaN theoretical limit, but the commercial devices are somewhere here. There is a big gap here, right, and this big gap is attributed to reliability, which is why while it was projected back in 2014 that GaN will replace silicon by 2020, it has yet not replaced silicon because of lot of apprehensions from the customers and from the system manufacturers. And that gap, this push has happened because of this big reliability gap, and if we address this reliability gap, we can basically get GaN devices to market, and that's what we are trying to address. So earlier we did a lot of studies, and we have made a lot of understanding on the GaN reliability part. I mean, these are some of the setups that we built. We do a lot of these complex integrations and different kind of experimentations, and now in phase 2 what we are also trying is, we are trying to basically dig deeper into transient reliability. What has been seen is that the GaN reliability is different when you study under steady state conditions versus transient conditions. So building a different kind of setup where we will emulate the system kind of stress scenarios, and using that we basically study the transient reliability. And another setup that we are building is transient interferometric mapping setup, where we will probe the transient heating effects all the way down to nanosecond time scales under these scenarios, and study the thermal evaluation or evolution across the system. Thank you very much. Happy to take your questions. So it does. So basically what we did, we developed a cyclic process. So so in this process what happens is that you basically oxidize GaN and then remove GaN, right. So and then it stops there. Then again you have to oxidize and remove, and this oxidation is also basically surface limited. So you basically oxidize just the top layer and then remove it. So now if you develop this process, then the variability is significantly reduced. But if you use standard chlorine BCl3 kind of chemistries, the variability is huge and you cannot control it to that extent. No, these are deep acceptors, so they don't basically there is no interplay between these deep acceptors or the holes present inside the aluminum dioxide with with the device. More importantly, this is sitting far away from the active region, right. So there is no interaction between, say, the electrons or the hot electron, even if they have hot electrons, with the holes present in the aluminum dioxide. So we have done a lot of investigations. Even you can talk to Rajeshri and Vipin here. They are now doing a lot of transient reliability investigations, fast pulse investigations. Vipin also does a lot of hot carrier simulations, and we have found this configuration quite stable, even in all these extreme scenarios.
Long live India and France friendship.